Hi everyone, hope you're all keeping well. Just a quick video here just to kind of go over some of the stuff that we talked about during our live lesson today to do with semiconductors. So the learning intention to explore this concept of semiconductors, and hopefully by the end you can define kind of what a semiconductor is. I can describe the difference between a conductor, an insulator and a semiconductor, and I can discuss the movement of charge in a semiconductor. So conductors and insulators we should hopefully all be familiar with. We have our conductor. Our conductor, the electrons are able to flow easily through the medium, and as such the electrical current flows. Essentially that's what the flow of electrical current is, that easy movement of the electrons through whatever medium we're talking about, whatever kind of type of atom or whatever compound we're kind of looking at. Insulators, on the other hand, the electrons aren't free to move easily in the medium. So it's got very few free electrons, and because these electrons are quite tightly bound, the current isn't able to flow easily in insulators. I will say it isn't impossible for it to flow. We do see situations in our everyday life where electrical current will flow through an insulator. The problem is it tends to destroy the insulator in the process, which is kind of why they're insulators. The example I'm talking about, of course, is lightning travelling through air. Obviously we don't see lightning every day, but lightning is a form of electricity, and its electrical current is going to travel through the air, and essentially it's destroying the air molecules that it's passing through in the process. So this new one that we're talking about then, semiconductors. Semiconductors behave like an insulator when pure and under normal circumstances. However, if we do certain things to them, we can change the way they behave, and they're going to actually start acting like a conductor. So essentially a semiconductor will behave like an insulator some of the time and will behave like a conductor the rest of the time. So some examples here, if we add an impurity, so if we add something else, for instance a different type of atom to the semiconductor, that can cause it to act like a conductor rather than an insulator. Or of course, if we just add energy, we can add some energy. It could be from a light source, could be from a heat source, could be from some other source. It could just be pure electrical energy, I suppose technically. Could potentially do it as well. Light source and heat source tend to be the kind of common ones that we would add to kind of cause that to act like a conductor though. So the structure of the atom, a little bit of revision first of all. Our atoms are made up of protons and neutrons. That is our nucleus, hopefully you all remember that. So protons and neutrons in the centre of the atom, tightly bound together, no space between them, they're really close, they don't want to separate at all. And then of course we've got this cloud of electrons which are orbiting the atom. Okay, now we've not really talked about this beforehand. However, the bit we're going to introduce just now, these electrons aren't just able to just kind of fly anywhere they like in that cloud. They've got to be in certain positions. So I mean, we call these energy levels. We tend to represent the energy levels like you see here. So the energy level here would be the lowest, the energy level here would be the highest, and they might go on higher than that, but this is just, I've kind of represented the energy levels of this atom just with 4 energy levels entirely. Well, energy levels essentially will kind of continue going on to for a long time yet. So they have to be in these discrete energy levels. They can't be anywhere in between. Now this energy level here is the bottom energy level. It's going to be the one closest to the atom, and then as we move up energy levels we are moving further away from the atom. So in the case of our atom here, we've got an example atom here, the electrons are going to sit here. They're going to want to sit on that lowest energy level. They want to be closer to that atom, as close to that atom as possible. If we were looking at another atom, a bigger atom with more protons and more electrons, then we could start to build up. So we might have another electron. We'd have 2 in that bottom rung there. However, the next ones would start filling up the next energy level. And the reason for that is we can only have so many electrons on an energy level at a time. And I don't want to say too much more about these energy levels. We'll come back and look at that when we're in the next unit. We'll talk more about energy levels in atoms and quantization. However, just some brief notes just on this one here. Electrons can only sit on these distinct energy levels. They can't be in between the energy levels. If one were to try and jump up to the next energy level and not quite make it, it would fall back down to this energy level here. If it were to jump up to the next energy level, it can sit on that energy level for a period of time. However, it's going to want to drop back down to its original energy level eventually. Again, we'll talk more about that later. Each energy level can only hold so many electrons, and the electrons are going to try and fill the energy levels starting with the lowest, so that's the one closest to the atom. So why are the conductor, the semiconductor, the insulator, why are they all different? Why do they behave differently? What's different about them? Well, when we were talking about our energy levels a few seconds ago, what we actually tend to think of them as when we're looking at semiconductors, we tend to think of these energy levels as bands. Okay, so we have bands of energy where those electrons are going to be sitting. So we have our insulator, our semiconductor, and our conductor. Each of these are going to have a band or bands of filled energy levels. These are the energy levels that are all completely full. They couldn't take any more electrons. These all sit down closest to the atom, and because they're all full and it's the same for every atom, I'm going to just get rid of this. I just wanted to make sure that you knew that they were there. So there's going to be electrons in these lower energy levels. These lower energy levels will be full. So we'll get rid of that one there. Now, what we have, or what we also have in each of these, is we have what's called a valence band. So this is the valence band here, and the valence band isn't full, or might not be full. Obviously, each atom has a valence band. However, there's another band, and basically what we're going to be looking at is the kind of difference between these two bands, and that's what makes the difference between an insulator, a semiconductor, and a conductor. So the next band above the valence band, this would be the furthest out band that you could get, is called the conduction band. Okay, now just for clarity's sake here, what I'm going to do is I'm going to get rid of all these words here, just so that we can kind of see this all nice and clearly. However, up in the top corner there, I've just put a little key just in case you forget which one is which. So the black is the valence band, and the purple is the conduction band. So when we look at our insulator, we see here we have our valence band here, we have our conduction band here. So what we have is we have a large gap between the two, and that's what makes it an insulator. Because there's a large gap here, it's very hard for the electrons to jump from your valence band up into the conduction band, and if they're not in the conduction band, it can't conduct electricity. The electrons need to be in the conduction band in order for it to conduct electricity. When we look at a semiconductor though, we find that the conduction band tends to be closer to the valence band. So we have a smaller gap. That kind of makes sense. It's a smaller gap. It's easier for it to jump. So if we add some energy, either by using a light source or say some heat or something, we can cause some of the electrons to jump from our valence band up into our conduction band, and our semiconductor can then conduct electricity. Very useful. Why is a conductor though? Why is it able to do it freely? Well, you may have guessed this already. The conduction band and the valence band, they both overlap. So conductors and insulators and semiconductors, this is just a kind of text of what's different, just so you've got a note on these. These will be in the PowerPoint, which I'll put up in Google Classroom as well. So an insulator, the valence band and conduction band have a large gap between them, which prevents the electrons from moving into the conduction band. Semiconductor, the valence band and the conduction band have a smaller band gap between them, and this allows, with a little bit of energy, a little bit of extra energy, the electrons to make that jump into the conduction band, and it allows for the conduction of electricity. The conductor, the valence band and the conduction band overlap, and this of course allows electrons just to flow freely, and that's what allows it to conduct electricity. So semiconductor bonding, this is kind of what semiconductor bonding looks like, okay? So what we've got here is we've got our positively charged nucleus, okay, represented by these red spheres here, and we've got our little negatively charged electrons. Now, the outer shell is going to want 4 electrons, So this is for our bonding here. So for our valence band, we're going to want 4 electrons in our outer band. So we've got 1, 2, 3, 4, which will belong to this atom. Then the other ones here, so this one here would belong to this atom, this would belong to here, this one would belong to this atom, and this one would belong to this atom here. Okay, so that's why we've got 2 here. And this is how the atoms essentially are bonding. Now, the trouble we've got is obviously, we talked a little bit earlier about adding impurity. Now, what happens if we add an impurity? How is that helpful? How can that cause it to conduct electricity? How can it allow electrons to flow essentially in our circuit? Well, let's imagine we've got a little impurity here. So I'm going to change this atom here, okay? And I've just made this blue just to highlight it. Let's pretend that this is a different atom in our semiconductor at this point in time. Okay, now if we've changed this atom, what we would do, in particular if we were wanting to make this, we would make sure that this atom didn't have a completely full outer shell, so that all the electrons in that outer valence band weren't full, and we might end up with a little gap. So a little gap, as you can see here, we've got 1 electron now missing here. We call this a hole. Okay, so this is an electron and this is a hole where that electron should be. Now, what's useful about this is we now have this little hole here, and this hole is free to move around, so it can swap places with an electron somewhere else. So this hole could move over here, and this electron would move to fill the gap. If we've got a hole here, it could then move over here, and this electron would move to fill the gap. And the hole and the electron are going to move places, are going to change places as this happens. Now, what's useful about this, what's really useful about this is the electrons obviously have a negative charge, but that hole essentially acts as a positive charge. So we can see here that I've just kind of made it red just now because it's essentially acting like a positive charge. It's like a positive electron. I mean, if we could have such a thing. It's not obviously a positive electron, it's just an absence of an electron, but it acts as if it were a positive charge. However, it's just this hole that's there. So that's what essentially happens here, and this is why we are able to get some conduction if we add an impurity to a semiconductor. At this point, I'm going to leave it here. We're kind of about ready to move on to PN junctions. We're going to look at that in our lesson, which we'll be looking at today. We'll do a bit of a live lesson on that one on Google Classroom, and then I will post something kind of similar to this afterwards, okay? So just to recap on our success criteria, I can define a semiconductor, hopefully you're there. I can describe the difference between a semiconductor, an insulator, and a conductor. I can discuss movement of charge in a semiconductor. That's us. Tune in later for our, or earlier possibly, depending when I get this posted, for our live lesson, guys, and we'll go over the PN junction and we'll look a little bit at diodes as well. Okay, see you then.